Good deal. All right, well, hello everybody. Welcome to the June installment of VAST, Virtual Astronomy Software Talks. This is a monthly meeting where we have usually two speakers talk about some open source software, do some kind of astronomy work or something that they're working on or they're interested in. And today we have Kyle Oman, who's an associate professor, doing research in the Department of Physics at Durham University in the UK. He's written numerous software packages, including Martini and GravSphere, which is a genes modeling code. And today he's going to talk about SWIFTGalaxy, which is a galaxy particle analyzer. So he'll talk for about 20 minutes or so, and then we'll have really the rest of the time today for discussions, or as much time as people want. And when that happens, we can think of some things to talk about if people are interested. So with that, Kyle, you have the floor.
Thanks for the intro, and for reminding me that I've contributed to GravSphere, although I think it was a whole one line of code. So I did write Martini, though, that was true. Right. Yeah, so this is the first time I've interacted with the VAST, so I haven't actually attended before. So it's a little bit of a shot in the dark in terms of where I pitched this and how this is going to go. But hopefully, yeah, people find it interesting. So I can put up some slides. And now I've lost all of you on the Zoom. Oh, I'm not sharing screen, that's why. All right, now you should see the slides. Good. Okay, so yeah, this is about SWIFTGalaxy, which I'm just now in the process of putting this through the PyOpenSci review process. So it's got to the point where it's mature enough for at least having a go at getting it peer reviewed. And it's also picked up a lot of users very quickly as we're using it in a large collaboration around some new simulations that are just coming out, and I can touch on that. And so the idea with this package is to try and take care of some tasks that people who work with simulations of galaxies, basically everyone ends up writing their own scripts to do this. And I think everyone writes just about the same script to do this. So packaging some of that up into a coherent place, and then also adding on some nice quality of life features if you want. And so this was really born during my PhD now 8 or 9 years ago, when I started writing my own collection of scripts. And then about 3 or 4 years ago now, I started porting over all the ideas that I picked up in that process to this package, which is built on top of another one called SwiftSimIO. So I'm going to start with a fairly horrifying slide. I debated whether to actually put this up or not. It looks like spaghetti. But I think sometimes it's nice to look under the hood a little bit. And so this is my take on kind of the pipeline, if you want, for a big simulation project. And so I know observational astronomers love their data reduction pipelines, and how you get from the raw imaging on the telescope down to your data products in the end. So this is a little bit analogous to that, but now for a simulation project. And there's various different bits in it. So we'll start at the beginning, which is on the top left here. So if we want to do a simulation, we need some initial conditions for that simulation. And I'm not going to dwell on all the details here, but basically we have, in this case, one of the projects I work on, we have constrained phases. So this is like information that's going to allow us to make a piece of the actual local universe. That gets fed into a code that actually generates the initial conditions. So this is like, okay, we know the cosmic microwave background power spectrum. We impose some constraints on that, and we're going to get a particle distribution that we can then integrate through time. And that spits out, okay, your initial conditions for the simulation. That goes into some kind of simulation engine code. So this lower left area is where the actual simulation happens. In this case, the simulation code is called Swift. And this particular project, we're using a galaxy formation model called Colibri, which is implemented in that code. Other codes you might have heard of, so Swift, an equivalent would be like the gadget code or a repo or gasoline or Ramses. All of these are different basically gravity and hydro solvers. And then there's many different implementations of galaxy formation on top of that. So the initial conditions go into the simulation code, and then that produces snapshots. And so that's a picture of what the universe looks like, full of its galaxies at different points through time. And then we get into the post-processing area where lots of action happens. So once we have our kind of raw outputs, then in this case, we're feeding those snapshots into a structure finder. And so the raw outputs basically just have tables of many, here are lots of particles. The structure finder will group those particles into things that we would call galaxies. And that spits out membership files, which basically say this group of particles corresponds to a galaxy, this other group to another group. And that gets bundled up into sort of a set of virtual files with basically symbolic links between these two things. We then feed that into this other fairly new code called SOAP, which gives you nice, clean catalogs, like as the name implies. Like it's actually for spherical overdensity aperture processor or something like this. Don't quote me on that. But this is what's going to spit out now. Instead of lists of particles, we're going to have lists of galaxies. And so we'll get a catalog of galaxies in the simulation. We'll have galaxy 1, it has a mass, it has a luminosity, it has star formation rate, photometry in different bands, whatever you want. Okay, and so then that's kind of our simulation data set, right? We've got our snapshots and galaxy catalogs. And then we get into the analysis bit, which is slowly getting over to where the code I'm talking about today fits in. So our low-level interface is this SWIFTGalaxy code, and this knows how to read both the catalogs and the membership files. And as a user, you could talk directly to SWIFTGalaxy. This would be kind of like a low-level interface if you want. Or as another layer on top of SWIFTGalaxy, which gives you an interface to these files, you have SWIFTGalaxy, which basically glues the two parts together. It takes your galaxy catalog and your particle data, so your snapshot files, and treats those as sort of one database that you can interact with. And so the upshot being that you can tell SWIFTGalaxy, I would like galaxy number 7, please. And it will go and get both the particles and all the properties of that galaxy for you and give it to you in a nice, user-friendly interface. And so as a user, you can sit here and work directly with this code, or this code will then feed into other codes. And so, as mentioned, I wrote this Martini code, which makes 21 centimeter radio mock observations. So it'll ingest things through that. And so you'll basically say, well, I would like an observation of galaxy number 7, please. And then that'll feed back through here to go and actually get the data. Okay, so that's just kind of to set the stage and give you an idea of that this is one piece in a long chain. And so SWIFTGalaxy is built intimately on top of this SWIFTGalaxy thing. And I'll try and give in 5 bullet points what that code's about. So the most important thing it does is get information off the hard disk efficiently. Right? So you have a simulation with many particles, and the outputs have been written in a way that is not a random order, but the particles are written in a specific order so that particles that are spatially close together are also contiguous on disk. And so we call these top-level cells, and that's what's illustrated in the plot on the left here. So you see kind of the cosmic web in the background grayscale, and then the particles that make up this cosmic web structure are grouped together on the disk in these cells. So all the particles in each box are written as a contiguous block. And SWIFTGalaxy basically understands how to query that without having to worry about the very low-level files on disk. And along with that, it has some nice features, right? So there's a lot of metadata attached to the data itself, including physical units. And so it will return your data with here are coordinates in megaparsecs, here are masses and solar masses, and so It's also aware of cosmology, so if you want to think about co-moving versus physical distances, it handles that. And we have a visualization module that does efficient generation of images. And then the kind of colored blocks here are hinting at what SWIFTGalaxy can do. And so part of what goes on under the hood is to say, well, I'd like a galaxy, which corresponds to a little bright patch here. And so, I mean, the first thing to do is to say, well, okay, basically the smallest logical unit of data that we can read is one of these top level cells. So if we're interested in this purplish one in the middle here, well, we know where it is, we know its size, it overlaps with 2 cells, so we'd better read in those 2 cells to get the data that we want. But this, of course, all happens under the hood. And so, yeah, so just to kind of emphasize the problem we're dealing with here, right? I have a simulation, the Colibri suite that a lot of us are working on right now. Some of the bigger simulations have something like 10 to the 11 particles, right? That's 100 billion, that's a big number. And I want something like 1/1,000,000th of that data volume that belongs to one galaxy so that I can work on that and do some analysis before maybe moving on to a different one. Right, and then I also want to just generally live a happy, productive scientific life, so have a lot of the day-to-day headaches taken care of for me. And so this is actually an image, kind of pretty picture image taken from the Colibri simulations, where we can see some of the large-scale structure in the background here, with a field of view of a few megaparsecs. It's just a density map in the background, and then zooming in on a few interesting regions, so a cluster of galaxies and then an individual galaxy, and you see kind of the rich, fine-grained detail going on here, which is possible, of course, because we have zillions of particles. Okay, but if you weren't clever about how this was laid out on disk and how you were able to access it, picking out large but small relative to the total data volume data sets out of this could be quite a headache. Okay, so that's kind of the slides. I had a whole title slide and 3 slides. Then I thought I'd pop up a notebook and show just a little bit of the code in action. So yeah, this is on the GitHub. I picked the one that is running. So this one is one where it's meant as an intro for people with projects on this Colibri project where they have access to a particular system. There's a generic one for if you're just a user coming in off the street and you want to see what the code does. There's another notebook for that, but this one just has somewhat prettier galaxies, so I picked it. And so I'll jump right in here and try and quickly walk through a few of the features and see what's going on. So here we're using actually the lower level thing, this SwiftSimIO package that SWIFTGalaxy is built on top of. And just make this even a bit bigger. There we go. And we're using that to load up one of these galaxy catalog files. And so here I said, okay, please load up a catalog. And now I'm just going to pick all of the galaxies in the catalog in some range in total virial mass. So I'm saying, give me everything between 10 to the 11 and 10 to the 12, 2 times 10 to the 11 solar masses. Right, and so that'll give me some list of candidates, and I'm going to pick the first candidate in the list. And here I just said, okay, print now where that is in the catalog. So this is galaxy number 21,326 line. So now I've picked a galaxy to look at. So you could, of course, make whatever selection cut you wanted to here to get whatever galaxies happen to be interesting. And then I can use this SWIFTGalaxy thing. Import the main class here. Then I've got a helper because we're dealing with a SOAP galaxy catalog. And so here I'm just saying, okay, please make me a SWIFTGalaxy. Here's my particle data file. Here's my catalog file. And here's the galaxy I want to look at. And this is all the information I need to give. This. I have not run the previous cell. Okay. skip over this, which is just some plotting code. Okay, and so with just that, I've now loaded in the particles that belong to this galaxy. And so if I go back to my PhD days where such codes did not exist, this was the first 2.5 months of the PhD was, okay, well, there's a bunch of HDF5 format files on the disk. I have to read those in. I have to filter out the particles that I want. Oh, I guess reading the whole thing and then picking out the ones in a region that I'm interested in, it's pretty slow. That takes a lot of time. But they're sorted in a particular order. Okay, lots of work to get to that. And now this all works in about 3 lines of code, which is nice. And look, where am I? Okay. And so then I've defined some function that takes that object that I've just created and uses the SwiftSymIO visualization tools to just make images of the particles that have been loaded in. Right, so spoiler, you saw the plot already, but I'll run it anyway. And we can see that this galaxy has a gas disk, has a dark matter halo, and also a stellar disk, and it happens to be pretty close to face on. And I've set this up so that the middle panel is zoomed out quite a bit. So this little box is the aperture of the other 2 images. So we have a big dark matter halo with a little disk sitting inside, which is, I guess, what you'd expect a galaxy to look like. And so then what else can we do with this SwiftGalaxy thing? So it's aware of the halo catalog on the back end, or the galaxy catalog. And so I can go and say, well, from the catalog, there's like SOAP defines hundreds of integrated properties of the galaxy. So like I said before, you got various masses in just about any aperture you could want, photometry, angular momentum. There's a whole manual of what's in there. And so here I'm just saying, well, go get me the M200 of this galaxy in solar masses, please. And it spits it right out. So it's nice. It basically does the querying of the catalog for us. We've already recentered, so you're paying close attention. You see this is at 0, 0. This simulation is a big, this one's a 25 megaparsec volume on the side. So this galaxy does not live at the origin, it lives somewhere else, but the code has gone and found the center in the catalog and recentered on those coordinates for us. Coordinate transformations are nice. And so this will rotate things if we ask it to. So here I'm just saying, well, the catalog actually tells us what the stellar angular momentum vector is. So we can query that from the catalog and then just use that to define a rotation matrix and say, please rotate this galaxy so that we see it face on, and then make the plot again. So it's close to face on before. Maybe I should have picked a different example, but now it's properly face on. And this is enforced to be so that all the particles always live in a common coordinate frame. This is like the most common pitfall, at least in my experience, is you load everything up, you rotate the gas, forget about the stars, and now you have a misaligned disk, and none of your plots make sense, just because you forgot that you actually have to rotate all the different bits of your galaxy together. And of course, once you're working in a coordinate frame centered on the object, you probably want spherical and cylindrical coordinates. So that's implemented in the code. We can go get directly spherical velocities, for example, in radial and azimuthal coordinate components, and just directly make a plot of that. So that looks like this, which if there's anybody into galactic archaeology, this is the same. You've heard of the Gaia Enceladus structure in the Milky Way or the Gaia sausage, right? It's the same plot. So again, a couple of lines of code, we've reproduced that figure and actually see that here's the stellar disk up here at higher density, and there's a lower density, some kind of stellar halo structure down here. Okay, neat. We can mask out particles. So if we're only interested in some subset of particles, that can be done. And this will mask all the properties. And so here I'm applying a mask in the coordinates. I'm saying throw out anything with a cylindrical radius of less, or keep everything with a cylindrical radius of more than 2 kpc, and then I get a little hole in the center of my galaxy. But I could equivalently mask in temperature, and then it would mask, select on temperature, and then I could plot the positions of those particles. Or with the same selection on temperature, I've also masked out the metallicity table. So everything's linked under the hood. And yeah, so that's kind of the user-friendly stuff. And then the other aspect is, this is still a little bit in development, but the first pieces are there. There's some tools to iterate efficiently. So if you want to look at more than one galaxy, we go back. This is going to be easier to explain here. We go back to this, right? You have various galaxies. All of these live in independent regions of the data. But you can imagine if I want to look at several galaxies that share a common group of cells, I should probably look at these together before moving on to one that lives in a different cell. And that's actually quite a tedious optimization problem to go through. So we figured we may as well do it once in this package, rather than let everyone deal with that headache independently. And then on top of that, we want to add kind of parallel processing options. So you say, well, we're going to offload all the galaxies that share a common region to one processor, and then another one will handle a separate region. That way we're efficiently splitting up the I/O and the processing. But that's all kind of ongoing. So that's kind of the whirlwind tour. Switched off sharing. Oh, there's some chat going on. Okay, just links to various things. All right. So yeah, hopefully that was somewhat interesting, give you a glimpse into the world of galaxy simulations, if that's not where you usually work, or how we do things in this particular project, if you're more familiar with that kind of thing already. And yeah, happy to chat or answer questions.
Awesome. Thank you.
Yeah, great. Thank you so much. I think Sam had a couple questions in the chat. Do you want me to read those, Sam, or do you want to jump in with them? And then I see one hand raised. We'll get to you in a second, Peter.
Yeah. So I guess the first one is, I'm just curious, the SWIFTGalaxy Python object, does it have like a dictionary that contains an entry for each kind of particle in the simulation? Is that roughly how it works?
So how's it structured? It's more array focused. So the main object you can think of, so one thing I didn't mention is we have a lazy loading philosophy. So the main object basically has a bunch of properties, which when you access them, will then go and read the data that you want when you ask for it. So that's a little bit dictionary-like, although you tend to access it through attributes rather than like a dot notation rather than a square bracket notation. And so there you're saying like, yeah, okay, so my main object dot gas goes into kind of the gas section, and then dot coordinates if I want the coordinate array, or dot temperatures if I want the temperature array. And then I say array because those are arrays. So we've subclassed the unit array, which is itself a subclass of NumPy arrays. If you've worked with AstroPy quantities, it's very similar. It's a different implementation of physical units, but it's all built on NumPy.
Okay, cool. Thank you.
And then I see the other question in the chat was, can we track through snapshots? That is coming. So something like 2 years ago, we decided to change which structure finder we used, and the temporal aspect is, well, yeah, we had to rebuild a lot of tools around the new structure finder. The temporal part is coming. That's definitely on the wish list. So there is not yet a like SWIFTGalaxy dot progenitor or dot descendant, but that is in the cards.
Okay, cool. Thank you.
Very cool. Peter, do you want to jump in with your question?
Sure. I sort of have two things. One was a minutia about the units. I saw that you defined it as the U in the module, but it looked very much like AstroPi. So what if I have a code that combines something with fits and I have AstroPi in it and your unit? Are they, I mean, why did we have to invent a new unit when AstroPi seems
So this unit, it's UNYT, and you'll notice the YT, which I think actually might predate the AstroPi quantity. Yeah, so we've extended the YT unit system just to support cosmology, so like co-moving and physical coordinates. That was a design decision that happened before I got involved, and I have pushed against that a little bit at times because I mostly prefer AstroPi. But it is compatible. So Martini, for example, is written in AstroPi and will ingest SWIFTGalaxy quite happily. So unit will export or convert to AstroPi quantities. That's fine.
Right.
So if you're an AstroPi user, you're left with the slightly annoying conversion step. But
would it make sense to put a couple of people together and see if we can convince AstroPi to absorb some of these new cosmology ideas that we need in unit? Do you see that it could be compatible, that it could be made compatible?
So yeah, I basically very recently completed that cosmology subclass of the unit array, which could be interesting to port over to AstroPi. I need to first forget how painful that was for a few months before jumping in. But yeah, I'd be interested to have that conversation. And we have floated the idea of like, it would be nice to offer a truly AstroPi compatible mode for this. That's just, it's a big piece of work that someone would have to do.
Yeah, you're not the only one, because if you look at AMUs, they have a whole different system of units there as well, where they use the pipe operator to assign units as opposed to the star. But I did notice in one of your code examples that you showed, the Cosmo quantity, the first two arguments were a value and the unit, as opposed to value star unit that I saw somewhere else. Is that does it imply that the data that you get don't have the units involved in your HDF data? Are the units baked in there, or do you assign it later by a rescaling operation? I have this kind of cosmology, blah, blah, blah.
Anything you read from the files on disk. So the HDF5 files, the way they store the data is they have tables, which are your raw numeric arrays. And then there's metadata attached directly to the tables, like logically in the file. And that contains what are the physical units, what is the cosmology, how do I convert, how does this thing scale with the redshift? All that kind of information is annotated and read in with the array. So I think what you saw is, if you want to correctly interact with the data that you've read in, then if you want to define a new constant, right, you say, I'm going to cut at 2 kiloparsecs. Actually, you have to say 2 proper kiloparsecs at redshift 0.3 or whatever it happens to be. And so that's what that Cosmo quantity is. So that would be very similar to an AstroPi quantity, but to construct an AstroPi quantity, you have the star. So you can say 2 star KPC. That's fine. I guess we haven't really considered whether you'd want a similarly simple question mark notation or interface to then say, well, these are co-moving megaparsecs at this redshift that scale in this way with the redshift. So we just use an explicit constructor, which is why you see the arguments like that. So that makes sense.
Yeah. I'll do a follow-up question maybe a little later after some more questions.
We have another in the chat that I'm happy to read unless Aditya would like to unmute and ask themselves. But they say, can you explain more about the dark matter halo around the galaxy? Do we see the dark matter halo in the image you showed?
Yeah, maybe I can bring it back to talk completely abstractly. Let's go to this one. Yeah, so these being simulations, we're not bound by the limitations of telescopes. So the simulations include, well, an assumed model for how dark matter is distributed and then how it interacts, which is basically just gravity. And so this, yeah, here I'm showing a density map of the dark matter particles in the simulation. Cut down now. These are the ones that are found by the structure finding code to be gravitationally bound, which is a slightly fuzzy concept, cosmologically speaking, but gravitationally bound to this particular galaxy. So I don't know if that answers the question. I guess become very used to thinking about dark matter. So I'm never sure if I've quite hit the right tone.
Feel free to ask a follow-up in the chat. Until then, though, I think we have someone else with their hand raised. Would you like to?
Questions. Does track stars as they're formed? So does it track star formation? Can we also make a plot for that? That's one question. And the other one is, can we use non-cosmological galaxy simulations? So for example, just two individual galaxy mergers as an input for your code? Thank you.
So the first one, the audio came through a little bit garbled. So if you could maybe recap that one. I heard something star formation, but that was about it.
All right. Sorry. I was asking if the code can track star formation. Essentially, can it also index newly formed particles?
Yeah. So the code will also, yeah, follow stars and those. I mean, a typical galaxy formation simulation will annotate the particles with their formation times. So you could very easily get a star formation history of a galaxy if you wanted to do that. I'm not going to try and do it live, but it would be just a couple of lines. And then the second one was, could you use this with a non-cosmological simulation? So yes, nothing wrong with that. This particular code is very tightly coupled to the Swift simulation code, just because it assumes it's going to find things in the output files, which is mainly the metadata. So most simulations write the same kinds of HDF5 tables, right? You'll have a table of coordinates, a table of velocities, a table of temperatures, and so on for every particle. But Swift is relatively unique in a slightly horrifying way in actually annotating all of the information you need to know what units those things are in. So I've worked on simulations where it is just assumed that you know that the masses are in 10 to the 10 solar masses and that the lengths are in H inverse megaparsecs and so on. And you just have to know or ask or guess or something. So yeah, for now, this is very restricted to Swift. Well, and it also, yeah, because it comes through Swift SimIO, there's also the assumption that the layout of the order that the particles are written in the table is very particular, which is not a universal convention. So we've debated back and forth, right? Could you like impose some standard on the simulation community? You could imagine like fits for simulations or something. That idea has been floated and has not caught on. No one's been able to kind of push that through. So yeah, to make this code perform as well as it does in kind of IO efficiency and things like this, it is tightly coupled to a particular format and therefore a particular simulation code. But Swift will do all kinds of things. If you want to run a non-cosmological Swift simulation, lots of people are doing that, and this code would just work just fine.
Thank you so much.
Great. We have another question from the chat. Kamal asks, a little off topic, but how do Swift Galaxy results compare to real observations? How well do they recreate them?
Okay, so this now depends on the simulation. So Swift is a simulation code. There are many galaxy formation model implementations in Swift. So you've probably heard of the Eagle simulations, if you've heard of any simulations. Those are now 10 years old. Those were run with a simulation code called Gadget, but that entire model has been re-implemented in Swift. So you could run a Swift Eagle. You could run, we're working on this Colibri model, which is kind of from the same group. There's a bird theme, I don't know where that comes from. And so that's a different galaxy formation model, which will produce galaxies with different properties than Eagle. There's a group that's put the Gear galaxy formation model into Swift. I think Ramil Dave is putting the Simba galaxy formation model, or its successor, is going to be in Swift. So there are different models which will give different galaxies. And then if you want to talk about observations, there's another step to do to get from, well, here's a list of particles and their properties, to here's how it would look through a telescope. So if you wanted to do 21 centimeter, you could use my Martini code, or there's people working on doing radiative transfer to get realistic photometry. So one of the new things in the Colibri model is that there's dust sort of included on the fly. So you worry about doing the radiative transfer. So my star particles create light, and that light propagates. If it encounters dust, it's absorbed and re-emitted at longer wavelengths. And then eventually that gets to a detector. So there's a lot of steps, even after you've done the simulation, to then turn that into something that looks like what you'd actually observe. And then, okay, you can ask how realistic are they? And that depends on, well, realistic according to what metric. They might look great in the optical and nothing like the real thing in the radio. Or they might look, yeah. So it depends what you look at, what your metric for is this a realistic galaxy is. And then it also depends on the galaxy formation model, because different galaxy formation models will make different predictions. So Swift Galaxy itself as a code has nothing to say about that. It is a nice tool that kind of sits in between the outputs of the simulations and getting to an image of a galaxy. So myself and others are using this as one piece of that tool chain to say, okay, well, get me the particles that belong to a galaxy, and then pass those off to some other thing that will make me an image. And then we can do science.
Great. Any other questions in the chat, or feel free to raise hands?
I think Peter might have had a follow-up. Yeah.
Yes. Thank you, Alice.
All right. I did have some question about when we combine codes. It's sort of related to my earlier question when I'm doing AstroPy, and I have this U object sitting in there, but Unit has that too. And it's related to the fact that in Python, most of the time, we have all our data in memory. Is that true for you too, Kyle? Or do you stream data through? When you have really large cosmology data sets, you said you can loop over galaxies, so presumably I focus on a galaxy. I get those 10,000, 100,000 stars for that galaxy, and those easily fit in memory. But presumably the whole big original cosmology thing will not fit in memory, and you have no need to do that. But there's a particular code in there that I'd like to use, and it's ready to go. The question comes up, how do you combine codes in Python when you're sitting in the same shared memory? I have this object of this galaxy with objects, and I can probably map that to something in AMUs. So then the question comes up when you have objects like the AstroPy units and your unit and perhaps other things.
You're basically worried about, are you going to duplicate the memory of all this data when I...
No, I'm not so much worried about that, because AMUs actually does that behind the scenes. When they run these codes, they have private memory space that sits on the machine, and they have the Python space. So they already have two copies in that sense.
Okay.
But it's more like when I'm having in one module YT code, Swift code, AMUs code. Is that something that has been exercised where people can combine these codes? And I mean, the alternative is to write the data to disk and start a whole new Python script that only works in that particular project. Right. So have we exercised things like YT, Swift, and maybe other things? Is that something that people do?
So I've certainly had reasonable success doing that. So using this, feeding into Martini, for example, which is AstroPy based. So you saw I have this U for the units, U dot whatever. My own habit is little u is unit and big U is AstroPy. And so they coexist happily side by side, and you can do you know, 10 little u kiloparsecs dot to big U kiloparsecs, and it will convert over. So in that sense, I think it's fairly interoperable, and certainly our aim is to provide the data in a format that is easy to then pass to something else, where probably you need a sort of thin shim layer that says, okay, well, my other tool is expecting an array in particular units or in a particular unit system, or whatever the kind of data structure problem happens to be. So there's a good chance you do need that sort of shim layer. And SWIFTGalaxy actually has that. So it works with the SOAP catalogs, which are very much a part of the Swift ecosystem if you want. But it also works with a few other catalog formats. And there's basically a thin layer that sits between whatever that catalog is and SWIFTGalaxy, and does the translation between whatever's coming in on the catalog side and whatever it needs to work with the rest of the Swift stuff. And it's not that much work. If you came to me with another Swift simulation that preferred a different catalog, so this happened with the Simba crowd. They said, well, we like this Caesar thing. I went, okay, what's Caesar? Oh, it's kind of YT-like, but it's a bit different from the SOAP catalogs that we use. It's very dictionary focused, for example. And so there's a wrapper around that, and it's not terribly arduous to do.
Yeah, and memory usage of Swift, was I right in thinking that most of the time you have relatively small objects in memory, not terabytes?
Yeah, the goal is to just read what you need when you need it. So this is this lazy loading approach. So if you're never interested in the temperatures of the particles and you never access them, they're never read. And then we have this concept of the top level cells, the spatial sorting of the particles, basically. The idea is you should always be restricted to whatever spatial region you're interested in. And then when we start iterating over galaxies, the approach is, well, we first read in a spatial region that is small enough that we're happy to deal with it and contains possibly several galaxies of interest. That sits in memory, and then we dispatch subsets of that into individual objects that can then be worked with before moving on to the next chunk that we're happy to deal with.
All right, thanks, Kyle. I've said enough.
I'd like to compliment you on your documentation, which looks very nice, and there's the link for anybody who wants to go look at it. So I'm pretty impressed with this.
This is comes in part from starting to go through the BiopenSci review. So they very quickly make you conform to something sensible before it goes any further.
Yeah, but I'd also like to critique that because I hate Python with their quarks. You do a help on a routine and the nice stuff is hidden in a quark and you don't know where that is. I run into that too many times. I haven't tried yours yet. I don't know if you're suffering from that, but it's a Python problem, not a Swift problem.
So I don't know, did you say quark?
If you use the quarks, if you pass on additional arguments, like let's say plotting, for example, you have a nice Swift plotter, and you pass all the rest on to the plot routine of Matplotlib, then you don't get documentation on all of these extra things, like how you make different colors and how you make different symbols.
Yeah, okay, I understand. Yeah,
yeah, that thing, and it just many packages suffer from that, and it just kills my introspective mind because it means that you actually have to read documentation.
Yeah, mentioning the PyOpenSci thing, I definitely recommend engaging with that if any of you have your own packages. It's I mean, take it for what it is, but the opportunity to have an independent reviewer just look at your code closely and give feedback is found it pretty incredible that you could actually just have that happen. So it's a nice initiative. And also sign up as a reviewer for that or JOS or these kinds of things. I don't know, I've done a couple of reviews and learned some things that way too. It's been a bit of fun.
Great. I'm not seeing any further questions, so can I pass it back to you here, Sam?
Yeah, that's fine. We've got about 7 minutes left or so, and so if people want to go, that's totally fine. One thing we had considered talking about in the extra time was that, sorry, I had it down here somewhere.
Using AI for coding?
Yeah, I'm trying to find your email. Oh, here we go. That's why I guess. Yes. Yeah, so using AI for software development, learning Git, documenting software efficiently, or any ideas for future vast talks that people, things people are interested in hearing about, please let us know, because we this is for you all, so we want to make it sure that you're seeing stuff that you want to see. So if anyone has any ideas, you can say them now, or you can email any of the organizers whenever you think of them. Those are all good options.
Peter has already emailed me the suggestion that we have a talk on AMUs, which I think would be a good idea, and I'm willing to try to get Simone to do one.
I took Simone's class in my master's. I would also be happy to reach out to him.
Okay, why don't you reach out to him then, Catherine? So that's yeah, I don't think we've ever had him present at VAST. So, but are there other topics that people would like to cover? Do those of you who are online use AI to help you with coding tasks, to do some software development? I know some do, some don't, but I don't know about the people who are online. No, okay.
I've been very reticent to jump in on that, but possibly for no good reason. I don't know.
Yeah,
I tried and it gave me garbage, so, or at least it's not the code I would have used, so I've shy away from it.
okay. So we had somebody volunteered an article to ASCL some couple of years ago. Hold on, let me pull it up. Yeah, let's go. So this is somebody who is a computer scientist. He teaches computer science. John Wallen, who's the director of computational and data science and professor of physics and astronomy at Middle Tennessee State University. So he wrote this article on, he does use it quite a lot. So I'm not advocating one way or the other. I'm just saying there is, I have used it because I've never written in Python before, and I had a Python script that needed to be fixed. So I ran that through ChatGPT and said, fix this to do this, and ended up with something that did work, but it was just a very small script. So
I used it once to try and learn how to use TIX, the LaTeX like image drawing package. I would say like draw a circle and see what it did, and then kind of figure out how to take it from there. And it helped a little bit, but I don't know. I think the tutorials and documentation were maybe faster.
yeah. I found ChatGPT very frustrating for some of the tasks I've tried it for. So I generally don't use it. But I did, but it did give me some usable, a usable code snippet that did fix the problem we were having.
There's some like refactoring tasks where I find myself doing something fairly repetitive and procedural, but that's also not quite just find and replace or fancier versions of that your IDE will do. Where I'm like, surely like my brain has quickly learned, I know exactly the pattern I'm implementing here.
Mm-hmm.
A machine should be able to do this for me.
Yeah.
But haven't made the leap to like, yeah, if I could tell it the rule that I'm applying, which is full of heuristics, then it would presumably be able to do it. But I don't know. Maybe it's either this is like a perfect thing for AI, or this is, I don't know enough about AI to understand that this is not what it's for.
I also think it depends on the language you're using. And, if there's really common languages everybody uses, I think it does a much better job. But if you're using other languages which are not used all that often, then I don't think it has enough knowledge to really write good code and to really help you out.
Yeah, that makes sense.
Okay, well, we're in the last minute, so in order to not keep anybody later, so let's thank Kyle again for having a great talk. And I think, I'm not sure if we have anybody lined up for July, but if we don't, we're going to try to get some people. So if you want to give a talk, or if you know of any, like a grad student or someone who gets some exposure and get them given a presentation on some cool software, please reach out. You can submit an issue on the VAST GitHub page. And yeah, thanks everyone for coming, and hopefully we'll see you in about a month.